Hey, what's up guys? Chung here again. So today, let's take a look at this LeetCode problem number 315. Count of smaller numbers after itself. So you're given a input of integers here, and you need to output another array with the same size. The value of each position is how many integers after the current index is smaller. It's smaller than the current value. For example here, so the first one is 5, right? So how many integers that is smaller than 5 on the right side? 2 and 1, right? That's why we have 2 here. And then when we move to 2 here, there's only 1 which is smaller than 2. So that's the 1 here. And no, so 6, same thing. 1 is smaller than 1. Sorry, 1 is smaller than 6. And then this is also 1. So the last one is always 0. Okay. So this problem, the naive way, of course, is a brute force. So basically, every time when we add index I here, we loop through everything. We loop through all the elements after the current index, and then for each of them, if it's smaller than the current one, we increase the count by 1, right? And we do it for each of the index. So that's the brute force, and the time complexity is obviously n squared, right? And with that brute force solutions, this problem will TLE, will timeout. Would- So that's why this problem is a hard problem. If it's only asking you to do a brute force search, yeah, I think that would be more like an easy problem. But since that 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 naive way or brute force way is timing out, so it ask you to find a more like a better solutions that can reduce this n to the square to, in this case, it's going to be a n log n, right? So to do that, we need to use some um, new data structure. It's called binary index tree, or the the Fenwick the Fenwick tree, either whatever you want to call it. Basically, instead of every time still we will be still looping through each element, right? We'll still be doing the n here. This n that is not, it's unavoidable, right? Basically, we have to traverse n. That's our base. But when it comes to the second part here, instead of looping through everything, since we have a tree structure, right? We have a tree structure here, and for this tree structure, every time when we in the tree, right? Since it's like either left or right, so for us to find the informations we need to I mean even for traverse the entire tree, the time will be log n, right? So that's why we're gonna use the tree structure to help us improve this time complexity. Okay, and then the question is now is how can we use the tree structure to help us storing all those uh, the count informations, right? So I'll give an example here. Let's say we have a 4, 6, 7, 8, 1, 1, 2. Okay. So another uh, another concept here is that in order for this tree to work, we have to traverse from from the end and then backward to the very beginning. Why is that? Because when we traverse the tree, right, we want to know because in this problem it asks us to find the smaller numbers on the right side, right? Basically, by the time we are at this, for example, we are at 9 here, right? If we didn't traverse from the back, and then at 9 here, we don't know the tree structure because remember the tree structure is from top down, so you have to start from the bottom, from the up, from the root tree, the root node, right? If we're traversing from the very beginning, right? And since we're getting all the numbers on its right side, there's no way we will know what's on our right side. So that's why for this problem to work, we have to be traversing from the right from the end, and then we traverse it backward, which means we traverse 2 first, right? Because we do 2 here, and then we add 1, we add 8, we add 7, we add them in this way, so that when we add 9 here, right, we can traverse from top down, and we know which direction we will be going. Okay, I'll show you how this works, right? Because okay, let's say on each tree node here, right? On each tree node, of course, we're gonna have saved the value of we're gonna save the number itself, right? Okay, so that's the number, and besides the number, what we also will be saving to this current node is the left, basically smaller number, and small count. So this small count means at this moment, at this moment, how many numbers on my left is smaller than the current number? Okay. So what does that mean? So okay, let's say for example, at this moment we have we're adding 9 here, right? Then the 2 here. So the top, this is 2 here, right? So for number 2, how many how many numbers are smaller than 2, which is on its left side? There are 2 here, right? So 1 and 1. That's why we have 1, 2, and 2 here. Okay. And then how about 8 here, right? So 8 is so basically that's the 2 here, and this is a 1. This is this is 8 here. Because every time when we try to build this tree, we're gonna try to build a binary search tree. So basically, all the numbers on the left side will be smaller than 2, and all number on the right side will be greater than 2. Okay. So and for 8, how many how many numbers on the left side is smaller than 8? It's 3, right? That's 4, 8, 7, 6. That's 3, right? And so on and so forth. And when we add this 9 here, we'll be traversing. We'll first try to find a position for this 9 here, right? In this case, so for 2, we'll be going to the right side, and from 8, okay, so 9 is also is still greater than 8, so we'll also go to the right side. Basically, this is 9, right? And for at the beginning, there's nothing on the left side, right? So how can we use this binary tree to help us to find the which is smaller, the smaller counts on the right side, right? As you guys may have already seen, got the idea here, right? So every time when we traverse, go to the right side, right? Because if we go to the left side, we don't know. We don't know because the current number is smaller, it's greater than the current number, so we are not sure what's the total number and it is smaller than the current number. It is only when we go to the right side then we know. Okay, so since the current number is greater than this node here, right? And the number stores in this node the numbers here, which is smaller than the current node, will definitely be even smaller than the current number here, right? So that's why every time when we uh, traverse to the right side, we know this number, this 2, plus this node itself will be part of my result, right? So basically, so when we have 9 here, okay, so first we traverse from 2 to from the node 2 here, right? And 2 plus 1 plus node itself, right? And then plus what? There are like three which is smaller than there are 3 numbers which is smaller than 8, so which means there will be a 3 here, and this node itself is 1. So the total number in this case is going to be 7, which is a 1, 2, 3, 4, 5, 6, 7 for the 9. Right? Basically, there are 9 numbers which is smaller than 9 on the right side. So so another thing is we notice, so there won't be any double countings in this case. Why? Because this number here, the second number, is only the smaller number on the left side. So in this case, because let's say there's 2 here, right? 2, when it reaches to 8, it will stop. Basically, 2 will only store the smaller number uh, up to 8, and all the other smaller numbers than 8 will be stored in the node of 8, right? So that's why we can use this node to help us calculate the numbers. And another thing is the duplicate, right? So that we might have some duplicates for 2 because it's not guaranteed that we always have a unique number, right? So that's why every time not only we need to store the left a small count and the current values, we also need to store the count for the current node in case there are more than 1, 2 get in the array here. So here instead of 1 here, we will be adding like the count of the current node, either 1, 2, 3, right? Same thing for this one. And when we traverse, since this is the left side node, right? The left side small count, and every time basically we already said on the right side we will be collecting those numbers to be our result, and when we go to the left, every time when we go to left, we'll update. Basically, we increase this number because every time we have a new number, so okay, when we see we compare with the current node. If it's smaller than the current node, then we know we need to update the current node left small count to increase it by 1 because we have another number that is smaller than the current number. Okay, that's how we maintain this tree node and how we can use this tree node to help us calculate our final result. Okay, cool. So, okay, with that being said, let's try to code these things up. Okay, all right. Hmm. Okay, so like I said, since we're creating a tree, I need to create a new type as node here. Okay. Uh, okay, class node, and I'm gonna define some variables here. Okay. The first one, of course, is the value. So basically the value is the value, right? And the second one is I'll do a the count. What is the count? Smaller. Mm, small count. All right. 0. And then the count for itself. Okay. Then we have a left and right, right? That's standard for the tree, right? Basically, that's the definition for this node. The value itself, how many numbers is smaller are smaller, are smaller than the current value. And then the count itself, because we're using a value. We're using a value to represent the node itself. So there could be duplicated values, right? So that's why we have a count here. And okay, and then we're gonna have like create a helper functions called insert, right? So the insert is gonna be the node and the number. Okay, so that's the helper functions. Basically, it means at the current node, I wanna insert the number. Okay. Mm. Okay, so now let's code the main structure first. Numbers and so first we're gonna have an answer here, right? Since we're going to traverse from the backend, from the back, uh, let's initialize this answers array first. So it's gonna be n, right? For I in range n minus one, minus one, minus one, right? Basically the answer, right? The answer I here will be do an insert. We'll do an insert of the mm, node. Yeah, actually we don't need this node here. All we need is a root. Okay. So the root is the first element. Okay. So the root is the first one, which is the nums minus one, right? So we're gonna create a root first with the last element. That's gonna be our root here. And every time we'll be inserting into this root, starting from the root. Okay. And okay, so node. Yeah, and here in the end we simply return the answer here. Okay. And yeah, since we're getting we'll do a sanity check here. Basically, if not nums, we simply return uh, none as well. Okay. So now, uh, when we insert into this node here, right, we will basically we'll try to traverse the tree, right? So when we'll stop traversing, basically while the node dot value is not equals to number, that's when we stop traversing, right? Because we already find the node. And okay, so if node dot value is basically if the number is smaller than the current node, okay, then we know we need to update the node. Uh, uh, okay, then we know we need to go to the left, right? But at the left, we'll also check if the left has a node or not, basically, right? So if there's nothing on the left side, we simply just need to create a new node with a current number, right? Basically, if the not node left, right? Uh, we'll do a node left equals to new node with current number, right? And then like I said, we will do a node dot small count plus one, right? And then we will okay. Okay. And then we'll keep going node until node dot left because we will be keep moving to the node so that we can stop here because in the case of there's nothing here, right? There's nothing on the left side. We create a new node here, and then we also need to update this node with the left node itself so that when we reach the second while loop here, it will stop because at this moment the node itself, the node is the node that we just created with this am. Okay. Else, right? Else is either the same or the greater than the current value, right? So if it's the same, uh, okay. So when it's the same, it's fine because we already have this one here, so it won't be the same inside here. And so the next one will be a greater than the current node, right? So in that case, we'll be collecting do a sum here, right? Equals to 0. So the sum is gonna be the node dot small count, right? That's everything plus the count itself, the node count itself, right? And then same thing if not node dot right, we do a node dot right equals to a node sum, right? And then we do the same thing, node equals to node right. Okay. And every time when we finish doing this, we simply do a self dot count, so not self, sorry, node dot count plus one, right? Uh, because at this moment, the number is the same as the node, right? So that's why we increase the count by one. And then in the end, we simply return the current sum, which is the everything we have traversed, right? We have traversed, which is and plus the current node left count, right? Because at this moment, right? So we are adding this number here, right? And yeah, so every time when we add a new number here, so once we reach here, we already have the yeah. Do we need to add this node left count here? Okay, let's try to run it first. Let's see. Hmm. Okay. Small count. Uh, maybe here. Okay, so do I need this small count? I At the beginning, there's nothing here. I think I can just simply return the sum here. Okay, node dot. Yeah, I think we need this node dot small count because even though, let's say, there's the new node, when we add the node for the first time, it's this one will be 0. But let's say, for example, we have a like this 1 8 3 4 5. Okay, and when we add 8, right? And let's assume we have 8 here, and then we have another 8, right? So basically, when we add 8 at the first time, we'll be having like 1 here, right? Because under the node dot small count will be 0. But when we and then down the road, when we add 5 6 4 3, this 8 dot small count will be updated to 4 in this case, right? And then when we add 8 at the second time, since we're adding to the same, we're adding it to the same node itself, because when we try to add the 8 here, okay, the current node, when we are at 1 and then it's not the same, and then we go to 8, so the 8 is there, and we just want to return, the will return. But at this moment, not only we need the sum here, right? But we also need to see how many small count at this moment, right? It's on the left side of 8. That's why we need to add this node small count here. Hmm. Yeah. Okay, so I think that's pretty much it is for this problem I want to talk about. I know it's not a good explanation, even though even for me, I'm kind of I was confusing for a long time. And yeah, I think for you guys, if you really want to understand how this binary index tree works, you can go online, try to find a wiki page, and then try to understand the idea and the data structure behind this algorithm. Basically, just like we're just utilizing the tree structure to help you reduce the time complexity from n to log n, right? While you are having this tree structure, you'll be storing some additional informations on the node here, like what we did. And yeah, cool. I think that's it for this problem. Thank you so much for watching the videos, and stay tuned. See you guys soon. Bye bye.